So how many people do you have normally?
It's 20. It's a great honor for me to present Dr. Bogdan Kosteny, a good friend of mine, and then we have worked together in the industry for a very long time too now. He is the director of R&D at Schweitzer Engineering Lab, and he was a professor too at TND at Texas A&M. So he has done a lot of that experience. He has got that experience, and he is a very well-known person in design of protective relays. He has over 200 publications. He has been well recognized in the industry. He's a fellow of IEEE, and he has been recognized as one of the leading people in the field of protection. So whenever I have any questions or anything which I don't understand, the first person whom I call and trouble is Bogdan, and he's always kind enough to reply. And when we started this course, I said it would be nice for me to not to talk about 1920 technologies and then tell you how relays work. It would be nice to bring in a person who can tell what is happening in the industry now. And then he readily agreed. And it's very nice of him that even in spite of his busy schedule, he always makes sure that he is available this day. He flies from Toronto only for 1 hour, 2 hours lecture here. And then it's very nice of him to do that. So with this, I welcome Bogdan, and we'll continue. Thank you.
Tab, for a very nice introduction. Thank you all for being here. It's a real pleasure to give that lecture. And before we start, I would like to make sure that you understand the type of talk we will have. So far in this course, you will learning about principles. You will learning what does it mean to protect the transmission line on a transformer, and then you learn about protection principles, meaning how to make a decision whether a protected plant is healthy or not within a couple of milliseconds using measurements from current and voltage transformers. So that went back to fundamental principles of electrical engineering, Kirchhoff's current laws, principles of distance protection or differential protection, which basically is applied mathematics, right? At some point in time, though, we have to cross the boundary and go back into the physical world, meaning that we need to build an apparatus, a protective relay, that will actually accomplish that function, that will follow the operating principle that you are learning about, right? And you have to realize that protective relaying started roughly 100 years ago, when we started building power systems, when we started interconnecting generation and building longer and longer transmission lines, and there was a need to protect it. What was the first protective device that you could name? It was a fuse. So people realized that if there is a short, the damn thing will burn. And we don't know where it's going to burn, right? So the smart thing to do was to say, if you are to burn, I want you to burn here, because I will know where to go, and then I will make that place easy to replace. So that's how they created a fuse, right? It's a controlled failure, in a way. High voltage power systems, they cannot be protected with fuses, so then we got protective relays. So what I do for a living is I design protective relays. And my background is power systems, so my starting point was protective principles but they learned enough about microprocessors, digital signal processing, the system approach to protective relaying, and so on. So let's go back and look at, where are relays in substations. So if you went on a tour or you work at the utility or you saw pictures, you know that we have this high voltage bulky stuff, transformers, transmission lines, and what have you. We cannot touch them because we are talking thousands and thousands of volts. So we have voltage and current transformers to do our sensing. We have circuit breakers to actually take an action if we see that there is a fault. We have tons of cables that run back to a control house because historically, and even today, we need a control house. We need a place to put that protection and control equipment and deal with it when we have to deal with it. And also to protect it from the environment and have things in one place so that we could access it. We are talking in a big substation, we are talking about hundreds of thousands of terminations. We have a three-phase power system, so we have 3 signals per connection. Then to bring a signal back electrically, we need 2 wires for each signal. And then the substation could be big, so it's not uncommon in a big substation to have 500,000 of terminations. When you bring those wires into a control house, you have to organize it, you have to label it. So sometimes we have the cross-connect racks when the cables from the switch yard are landed, and from there they are distributed to individual protection panels. Then we have relay panels when we wire all that stuff to protective relays and relays themselves. So this is a panel lineup with things like okay, let me try this. No, it's not going to work. With things like FT switches, those are for isolation of the wires from the protective relays. This is a protective relay, this is a protective relay, this is a protective relay, and control handles, and so on. So this is the physical environment that we are dealing with. Now, what is protective relaying? Historically, a protective relay was a single function apparatus that followed the simple operating principle, such as overcurrent or overvoltage or undervoltage, meaning that if you applied a current to a connection to a relay and you went above the pickup value, the contacts will click. Today, you could see those relays you used to see them in cars. Right now, they are phased out because they are replaced by power electronics, by solid-state switches, right? But historically, that was a relay. And those relays were possible to build, 100 years ago. All you needed is a little bit of a copper wire, wound it around the core, have a plunger, and when you apply the field, the plunger will move, the contact will close or open. So that was the technology available at that time. Today, a protective relay is a multifunction apparatus that provides multiple protection functions. So you could have overcurrent, undervoltage, overfrequency, underfrequency, differential, all in one device. It also provides for control, monitoring, metering, recording, and other functions. And you could guess it's built on a microprocessor. It's all digital. So what is protective relaying? Protective relaying is a field of power engineering, I would argue, and it consists of a couple of things. It consists of principles. So to call yourself a protection engineer, you have to know what the differential function is. You have to know the principles of distance protection, right? This is, in a way, this is applied mathematics, so to speak, or basics of electrical engineering. Then another aspect of protective relaying is relay design, meaning you have people who are able to design those devices to actually follow principles, to be an actual differential relay or an actual distance relay, right? Then you have application practitioners that put those devices together to build schemes, such as provide a full protection scheme for a transmission line or a big transformer. You have to be able to do settings, meaning configure those devices properly for a given installation. Then you have to test them, you have to maintain them. So there is a whole life cycle, so to speak, of the technology, when you have to know the protection principles, build an apparatus, build a scheme, deploy it in the field, set it correctly, maintain it. So you will have different types of protection engineers. So what I do is I design those devices, I troubleshoot them, I invent new things about them, I go and educate people, prospective users, about the benefits of new things. Pratap's life is to configure, to set them, to figure out how to build them into a big scheme and do it in such a way that is maintainable and it could be maintained by the utility personnel for the lifetime of the scheme. So we have different kind of shades.
These notes will be available on the PDF copies will be available. So if I see some of you are taking notes.
Yeah. So today we'll talk about relay design. And of course, I'm not going to teach you how to design a relay. But what I hope to accomplish is to give you an idea what it takes to design a relay and hopefully connect some dots that you may have in your mind, but they're not connected yet. So for example, you are taking courses, some of you probably in digital signal processing or electronic design. And all of it comes into play into one discipline when you try to design a state-of-the-art protection relay. So let's go back in history. We typically talk about 3 generations of relay technologies. The first one, as you could guess, was the electromechanical generation. We are talking about stuff that was in service, state-of-the-art, 170 years ago, 50 years ago, but also today. So what are the fundamentals? Fundamentals are that you have an electromechanical apparatus. You have a little micro machine with iron core, with bearings, with the coil that follows a certain principle, meaning that you give it a current above the pickup threshold and the contact will close. So this thing will have bearings, springs, contacts. It's a Swiss watch made for protective purposes. It's constructed to respond according to the desired operating characteristic. So did you learn yet about distance protection? Okay, so you know that you could sense the apparent impedance. If you do IZ minus V against V, you will shape a Mach characteristic. So now forget about a transistor, forget about the microprocessor. All you have is pieces of copper and iron, and build me a distance relay. How easy is it? It's not easy. Now, build it so that I could adjust the reach. I could say, now it's 20 ohms, and I would like to move a knob or something and make it into 30 ohms. How do you do that? Right? So the disadvantages were that, those were expensive and relatively large, not accurate because they were not only analog devices, they were electromechanical devices with moving parts. So anything that moves, that has a spring or a bearing, you have to suspect that after a year or two on inactivity, it will get stuck, it will get dirty, there will be dust, there will be rust. How could you trust it? So we have to maintain it in a proper way. And also, what those devices could do was extremely limited by the construction. If you provide something by means of calculations in real time on a microprocessor, whatever you could dream, you could program. Anything is possible. When you are taking a pieces of iron and copper and building something that moves, your options are really limited. But that was the technology available then. So this is an example of a distance sensing device, courtesy of Mr. Warrington, a very known pioneer. You could look at the date. It's 1944. That was the invention. At that time, they had vacuum tubes, but they were too new a technology for this. So as you could see, there is a core, there is coils. You shape that thing properly, like this, and it will behave as something that you hit it with a current and a voltage, and it will respond like a distance relay. It will respond to a distance to fault, or an apparent impedance between your CTs and PTs and where the fault is, right? But it wasn't trivial. There was a lot of auxiliary switching, springs, bearings. This thing wasn't accurate, but that was state of the art. Now, guess what? If you go to a substation today, you will see electromechanical relays. Why is that? Because they were built very well and they last forever. If you maintain them, they will last forever. Now, on top of that, if you go to a nuclear power plant, when they are really over careful about software quality and all those things, they believe in electromechanical relays. Most of the relays around nuclear industry is electromechanical. And actually they enjoy it because, what's the cybersecurity concern about them? None. Right? What's the software quality concern about them? None. So there is still a lot of electromechanical relays in service, and those are examples. This is how they look. Those are little cages with those bearings, springs, and moving parts inside. Now, then people invented a transistor and integrated circuits, so we entered the technology of static relays. What that means is that you could shape the distance function by comparing 5-volt signals on a printed circuit board using transistor or op amplifier. And what that opened up was that we could afford more sophisticated characteristics because we could just pile more op amps or transistors on that board and we could shape more complex things. Relays got smaller, lighter, they didn't need that much power to run, and in theory they were better. Now, they were still analog devices, meaning that they could drift, they required calibration. The early days electronics was quite fragile, and the substation environment is quite harsh, right? There is extremes of temperature, there is electromagnetic interference. The reliability expectations from a relay are much higher than from a toy or a VCR that you could buy at that time, right? So, and that technology actually was a lost generation, so to speak. It never took off because it wasn't solid enough, and the microprocessor-based technology came just after that. You could still see solid-state relays. Some of them they have a high performance, meaning that in terms of sensitivity and speed, some of them were very, very good. Now, most of them were not reliable, but some of them were really fast. This is an example of a static relay, and you could see here that there is, you could see through that transparent cage that there is a low-density printed circuit board. There is dip switches for settings. If you wanted to move that overcurrent relay to respond from, say, 2 amps to 3 amps, you would move the dip switches. Those are the settings. It's modular, meaning that you could pack some of them and build a scheme, and you would interconnect that scheme on the back of the chassis, make connections between those modules that host a very simple function, such as a timer or an overcurrent relay or an undervoltage relay. You could mix and match. That was a pretty popular concept. It came from ABB. But again, it's a lost generation, so to speak. So when you look back at the principles and say a mode distance function, you know that you have a impedance, reach impedance. You want to reach up to this point, right? And you know one thing, that if you build a term current times the replica impedance, so I is the current that I am measuring right now, ZR is the setting, this is the point I would like to reach to, and you mathematically, to draw a circle, what you could do is, if you check the angle between this magic expression I times Z minus V and V, and you compare it with 90 degrees, the angle less than 90 degrees would be the inside of that circle. This is where I'm going to trip. And the angle greater than 90 degrees is the outside of that circle. This is where I want to block. So just running this equation in real time, I could build a distance relay, right? So now, an idea. How about using an analog to digital converter to digitize my current and voltage, sample it to the tune of 16, 32 samples per power system cycle, every millisecond or every fraction of a millisecond, use a microprocessor to calculate the phasor, the complex number that represents my current and voltage, then use the same microprocessor to just follow my operating principle, such as do the IZ minus V versus V angle check, whatever calculations constitute my operating equation, and then from a microprocessor assert a signal to a little electromechanical relay, a very generic relay sitting inside the same box, to close the output and allow the breaker to trip, right? So a very simple idea, and people were toying with this idea since 60s. They used mainframe computers to prove the concept. Literally, you will have a mainframe computer sitting at American Electric Power and the other one at Bonneville Power Administration, or PG&E, I think it was PG&E, proving the concept. And they actually could do a distance relay. It was ridiculous. Nobody would allow a mainframe computer to. It almost needed as much power as that line that it was protecting could deliver. But people were toying with it. Our company, we released a product in 1994, and we started selling it. This is one of the first microprocessor-based protective relays, if not the first one. All the manufacturers that were experimenting. Now, this is a classical case of disruption. If you study disruptive technologies, this is a classical case. When the old technology is so profitable and everybody is so comfortable that they will not pay attention to what's going on. So our company was started in a garage 30 years ago, literally. And we have more than half of North American market today. And since then, Westinghouse ceased to exist. Okay, and they were the powerhouse of electromechanical relays at the time. So a classical case of disruption. Now, the beauty of this is this. Once we use the microprocessor to do protection, what else can we do? Well, we could locate the fault. We could process that current and voltage and give a very accurate, to within a couple of percent, estimate where the fault is, so we could dispatch the crew and start fixing the line. We could put multiple protection functions in the same relay. We could do the wiring between the protection functions. We could build a scheme through programmable logic rather than DC wires between the contacts of discrete relays. We could do metering. We could do SCADA control. We could talk with a substation computer and execute commands and provide metering to the SCADA computer. We could change settings on the fly. We could adapt the settings based on the external conditions or on a clock. If this is winter, we could switch to one set of settings. If it's summer and the loading is different, we could switch to another set of settings, and so on and so on. I mean, sky is the limit. Once you put everything, when you converted everything to a set of calculations, everything is possible within the limits of the horsepower of the hardware that you have inside, right? So this is a view of a modern microprocessor-based relay. You have a local port. People like to have a local port to just plug the laptop and interrogate the device. You have simple annunciation telling you that, okay, I tripped from a distance function, or I tripped from a overcurrent function. This seems to be very simple and old-fashioned, but this is required because, this is not for PhDs. This is for technicians in a substation. When they are there, tired, and for a specific reason, things need to be very simple. They could always connect the laptop to that port and get all the information from the relay, including a recording of what happened with proper timestamps and what have you. But the first layer of communication with a human is the simple LED annunciation. You have LCD display to display metering and alarms and so on. Local control, you could change setting groups, you could close and trip the breaker. When you look from the back, this is where we get our signals. There's new concepts to bring the signals via optical fiber from non-standard voltage and current transformers. But the reality today is that we get our signals through copper connections. From a traditional current transformer, voltage transformer, so 5 amp nominal, 110 volts nominal voltage. So you see a lot of screws, and they are for CT inputs. Modern relays could take, say, 2 CT inputs for line protection. You could have dual CT input, and those are 3-phase inputs. You will have a lot of inputs and outputs. You'll need at least one output if you call yourself a relay. That output is trip. You need another one if you are doing a reclosing function to close the breaker. You may need a position from a breaker. You may want to talk to other relays in a very simple way through contact outputs and contact inputs. So you need a lot of I/O. But also you may have a couple of serial ports to run some special communications either towards other devices in a substation, towards SCADA, and also between relays for signaling instead of using a simple on-off connections between the relays. Today you will find a lot of Ethernet ports, and typically they will be fiber-based. The picture shows copper-based. Some people use it for bench testing. In a real substation environment, you will go for fiber rather than RJ45. You will have a BNC input for the IRIG-B time synchronization signal. You need an accurate notion of time from satellite clocks or other terrestrial systems to synchronize your clock so that your records are accurate and other measurements are accurate. You may have fiber-based communications to other relays. For example, this relay is a line current differential relay. It talks with another relay like that at the other end of the line, sending back and forth current signals. So this could be done, is done via fiber. Either you go directly to another end or you go to a communications network such as SONET using time division multiplexing. There is a standard connection between relays and multiplexers. So this is the back of the relay. Now, you have to remember, the reason I'm showing this picture, you have to remember that this is a dirty environment. And what I mean by that is not, physical mud or something like that. It's electromagnetic interference. You have conductors that carry thousands of amps of current. You have 500 kilovolt network. You have tons of coupling. You walk there with off-the-shelf equipment such as video camera, and the damn thing will reboot on you, right? Because it's not meant to deal with this environment. We are building relays using microprocessors. New microprocessors run on 1.2 volts, and we are putting them in this environment, right? So we have to be mindful. So what is the typical architecture on the inside? A microprocessor relay needs a microprocessor. So, okay, we have at least one, let's call it CPU. This thing needs to have memory to operate. Typically, that's non-volatile memory, lots of it for storing records. You have interposing transformers for voltage and current. Those are inside the box. Those are relatively small. And the reason we have them is for galvanic isolation. You have to have galvanic isolation between the wires that go all the way to CTs and PTs and couple all the stuff that is in a substation and the clean part on the inside of the chassis when you have relatively fragile electronics that must be isolated from it. So those transformers are inside the relay for galvanic isolation. You have analog filters and you have your A to D converter. This is where your primary data is coming from, right? So this is where our primary information is. This is where we are going to process it. What we do, and many other manufacturers do too, is we put a giant FPGA in between. And the reason for that is to move the data quickly from one place to another, from one memory location or one microprocessor to another, and also lift up and pick up some of the very intensive calculations that we have to do. You have to remember that we want to trip very fast. This is not that we will take a sample and we will take 5 minutes to figure out if there is a fault or not. This thing needs to process things very fast. So if we have to put something on the FPGA for the sake of having a calculation done within a couple of tens of microseconds, we will do that, right? The next thing is I may have DSP-like microprocessors for just data crunching. Some stuff is more suited to a CPU. So for example, what I could mean by CPU is I could run communication protocols, I could write HMI, I could run stuff that is relatively high level here and relatively slow. And when I'm calculating magnitudes and operating equations, and I have to run it at the, at the rate of once a millisecond, I will apply a separate DSP-like environment and do it maybe on the FPGA. Right now, what the new parts allows us, we have the quad microprocessor when they have four cores inside and they're optimized. So this is a new way to maybe optimize the internal architecture of the relay. I have my binary inputs to get the breaker position or maybe other critical signals. I have to have my outputs. This is how I trip. I may have my IRIG-B for precise timing. I have my serial ports. I have my Ethernet ports that I may route through an FPGA and ask my FPGA to be a simple switch, for example. What else do I need? I need HMI. I need power. I need power to run this stuff. I need probably 80 watts of it to run it. Now you may think, what's so special about the power supply? Power supply is one of the most challenging things to run because, again, it needs to be galvanically isolated. And what is happening on the input to the power supply is very nasty. You could have kilovolts of spikes, and all of that needs to be shielded and isolated. On top of that, it runs hot and needs to run without failure for 15 years. Okay, so power supplies actually is not a trivial thing. A hardware engineer who could design a good power supply, that's a gem. So what do we, on the physical construction, you put those things in a chassis. So what we have here is a power supply. Those are the current and voltage transformers for galvanic isolation. We put them at the bottom of the chassis because they're heavy. This is stuff that has magnetics in it, so iron cores in a power supply and those transformers. We have an input and output board. Then we have the FPGAs, microprocessors, memory, and so on. Serial ports here. What is in that cage? What do you think? What's in that cage? Why do we have a cage? Because it radiates a lot. It clocks very fast. So in this case, those are the Ethernet ports controllers because they run at 100 megahertz and there is a lot of pollution that they produce. You may have some other boards with communications. Sometimes the design is modular, so you could replace, for example, you could have a module that has copper-based or fiber-based Ethernet. You could have point-to-point communications and different modules that will have different interfaces, such as RS422 versus fiber, fiber of that wavelength versus another wavelength. So that's a physical construction. Our boards are, they're becoming, 6-7 layer boards, fine pitch. We use the stuff that is available. I mean, we cannot afford our custom microprocessors, and it wouldn't be smart. So we use stuff that is out there. Stuff that is out there is driven by handhelds today, which is good because, they're after low power consumption and performance, right? But they move very fast, and they are really, high pitch components and what have you. What I mean by they move fast is they introduce a part, they cache on it, and they obsolete it. Our industry, we are supposed to support this stuff for 15, 20 years. So a big part of our business is how you design for part obsolescence. Because we don't manufacture relays like iPhones that, you just crank 500,000 of them, you sell them for Christmas, and you move on, right? You keep selling those relays, and you have to guarantee effectively that what people bought today, they could buy 15 years from now. So what is inside that box 15 years from now is quite different. So how do you structure your code? How do you structure the device on the inside so you could deal with part obsolescence? Now, signal processing. So if you were to simplify it, you will think that it works like this. You wait for the next sample. So for example, you decided to sample your input signals at the rate of 2 kilohertz, right? So half a millisecond, you will take a new sample. So you wait for a new sample, you got it. Then, you do a A to D conversion. So now you got a number that represents your input. Then what you may do is read the binary inputs. If is the input high or low, asserted, deasserted, right? Those are your inputs. Then you do digital filtering. I may want to calculate a power or an impedance or a magnitude from those input currents and voltages. Then I would like to run my criteria signals, so magnitudes and so on. Then run the element logic. So if I'm a distance relay, I have to crunch some numbers in a specific way to be a distance relay, right? Then I run user logic. The user tells me, take this input, end it with that, run this timer, and then close this output, right? So then I assert my outputs. Now, outputs are physical outputs, such as relays, closing contacts. This is a communications-based output. I may send the message through an Ethernet port to tell somebody that something happens, but it's an output. And then I will wait for the next sample, right? That's the very generic, unified way you would build a digital relay. Now, this is only about the main protection function. On top of that, I may have tasks that have to do with HMI, with reading those push buttons, with talking with a SCADA computer or 3. It comes to me and say, give me the phase A magnitude, and I have to parse the message. I have to get my phase A magnitude, put it in a packet, and say, here is your phase A magnitude. So that's the nature of the multifunction device. But for protection, this is pretty much it, right? Now, except nobody does it this way. It will be too unnecessarily complicated. Instead of what we do is we break it into typically 3 loops. One loop is basically like a digital fault recorder, meaning that we decided to just get the image of what is going on in our input. So this is just about sampling. So I may run it at, say, 2 to 8 kilohertz. New relays could do it, say, at 8 kilohertz. And I will run it in something like an FPGA. And what I'm doing really is I'm doing A to D conversion, I'm reading my inputs, and I'm storing everything in memory. And I may store it for a couple of seconds. So then if somebody comes, give me a file that tells me what happened in the power system, I could do this. So this thing is like a recorder, right? Except that the stored data is also available for the real-time protection function. The next scan, so to speak, is about things like frequency tracking. So to make our measurements correct for the power signals, we have to know what is the frequency of the power system. Normally it's 60 hertz. It hovers around 60 hertz. It may change, right? So we have to follow that frequency to get the accurate measurement of things like power, impedance, magnitude. Then we do digital filtering to get rid of signal pollutions that could hurt us. We calculate our criteria signals, and those are the things like magnitude, power, impedance, angle of the IZ minus V term, whatever it is that we have to calculate for a given function, and we store it. And this is often done in a DSP type of device because it's really about data crunching. It's about taking a sample and doing something with it, right? It's no different than programming filters for video streaming, right? It's just data crunching at a very predictable, regular rate. Now, here, that process, I put 16 to 32 as a range, S over C. And S over C stands samples per cycle. So what we did as an industry is we ran this process at a variable rate. We track frequency, and we do it so many times in every cycle, power system cycle. Power system cycle is 16.66 nominal in North America, right? So we do it, say, roughly every 1 millisecond, but it's variable. If the frequency moves, that process moves. That's not the ideal solution, because if you ever program a microprocessor, you don't want it to be at the mercy of some other process. and start changing your execution rate, right? But because the changes in frequency are so small, historically this is what we did. That we allow the system frequency, as we measure it, to adjust our execution rate. And running it not at 8 kilohertz, but only at, say, 16 times at 1 kilohertz effectively, or 2 kilohertz around, allows us to do more, calculate more stuff. So this is typically done in DSP-like type of a silicon. And then the last one is the final decision making, meaning that we run the element logic. We check our IZ minus V angle against something else. If there is a timer, we time out. We run user logic, and we assert outputs. And this is typically done 4 to 16 pp over C. And pp stands for protection pass or protection scan, meaning that we check whether or not we should trip, make our final decision, say 16 times in a power cycle or 8. That new relay that I showed you, it runs at 8 protection scans per cycle. So roughly every 2 milliseconds we decide whether we should close the contact or not. It samples at 8 kilohertz. And it does data crunching at 32 times a cycle. So it has all those 3 rates, right? So this is how you do it. So you have your hardware. Now, the beauty about microprocessor-based relays, and I hope you realize that, it's pretty generic. If I am a distance relay or a differential relay or a motor relay, do I need a different A to D converter? No. Do I need a different microprocessor? No. So there is a nice thing about microprocessor-based relays that hardware becomes relatively generic. Now, for size, cost, and input-output requirement reasons, you will see different boxes. But what really differentiates those boxes is software inside that they run. Some of them, they run a thermal model for a motor because they are motor protection relays. Some of them provide distance functions because they are line protection relays, right? So, and we have our silicon to really crunch the data. We build that silicon for minimum latency. And now what do we do? How do we decide that we trip or not to trip, right? So I picked the simplest function possible, the 50 function, which is, you should know by now, a straight instantaneous overcurrent, right? If the current is above certain threshold that came from a user as a setting, you trip. You should do it because it's not 51, which is time delayed, intentionally time delayed. It's 50, meaning instantaneous. You want to do it as soon as possible. So all your scans, passing data from one piece of silicon to another, it's all optimized, so we are not wasting time waiting for data to move from one memory location to another. And now we want to trip. So we want to trip, so assume this is a pickup setting, and well, if we want to be a fast relay, send one cycle relay, this is not available. This is future. If we act on that stuff that I just removed, we are slow. We are not good. We are not competitive. So this is the data available to us, that assuming that we will trip in one cycle. But guess what? To close that output, the little clicker in the relay, that thing will need 2 milliseconds to close. So in order to finish closing after 16 milliseconds, my microprocessor needs to issue a signal to it 2 milliseconds earlier. So I'm going to take away a little bit. Then, after I got my data, I need to have some time to finish my calculations. So assume that I take full 2 milliseconds to really process the new stuff that I captured. So let me take away, again, 1-2 milliseconds. So in order to trip at one cycle, this is the data that I have available to me, right? So now that I confused you some more, do you remember what was the setting on the picture that I showed you? Yeah. So, shall I trip or not? Well, it looks like the peak is, 120, but you know about the offset. You know that if you hit the fault at the right point of wave, the first peak could be twice as high as the steady state value, a fully offset waveform, right? Is this the case? Yes? No? How do we know? So this is the challenge that we have, that, and people are racing and say, okay, I have a subcycle relay. Well, you build the relay well, so it finishes calculating stuff very fast, but still you have only a small fraction of one cycle to make your decision on, right? So how do we do that? Historically, people were writing tons of papers about phasor estimation. And that was about calculating, when you study the principles, you are dealing with complex representations of voltage and currents, right? Those are called phasors when you measure them. Phasor is just the really an imaginary part of a sinusoidal wave, right? To measure it, people invented the phasor estimating algorithms, and probably you could find literally 1,000 unique papers written in the last 30 years about different ways to estimate a phasor. Do it accurately and fast. And you should say, I know how to do accurately or fast, but I don't know how to do accurately and fast, right? So the rest of big part of this presentation is that we shouldn't be looking at the Holy Grail. I design relays for manufacturers for 15 years now, and I was doing research for manufacturers before that for 10 years. And I know one thing, that those relays, they don't depend on any Holy Grail of the phasor estimator. It's something else that makes them tick or work well. So we will see how it works. So let's start with the phasor estimation. So phasor is magnitude or angle, or real and imaginary part. It doesn't matter. It's just the same information in two different formats. And for you, phasor is you assume a steady state. So you know that sine wave could be fully expressed with two numbers. So that's how the complex math comes into play. For somebody who builds a device, the challenge is different, that the thing changes on me. It has different things in it than just the sine wave. It has harmonics. It's distorted because maybe I have CT saturation, or it has this decaying DC offset. I am rushing to make a decision, and I want to estimate the real and imaginary part as fast as I can, and as accurately as I can. Because if I overestimate it, I will trip when I shouldn't. If I underestimate it, like a current magnitude, I will trip late or not at all when I should, right? So estimation is a process of calculating based on raw samples. So we know two things, that the sine wave has two unknowns. So in theory, let's just look at the theoretical, hypothetical analysis. I could take two samples, and because there is only two unknowns, I could solve for these two unknowns, and I will have my magnitude and angle, or real and imaginary part, correct? So then you tell me you want this fast, so how about you take those two samples a microsecond apart, and after a microsecond you will know what's the magnitude and angle, right? Well, it's not so easy. So typically what is done is you have your orthogonal filters. So you could run a simple IIR filter, FIR filter, with certain window, and you will get the real part. You run a companion filter that's called orthogonal filter, and you got your imaginary part. You could do it through a simple pair of filters that are orthogonal filters. So one, for example, could have a window in the shape of a cosine function, and the other in the shape of a sine function. Or here, for simplicity, you could have just these two windows. That one is just an average, and the other is effectively a derivative. Those are orthogonal filters. Each uses only two samples. Those are the windows, right? So present value and one sample back, and that's the present value of my real part. I do this with certain gain coefficient, and that's the present value of my imaginary part. If I subject this algorithm to a pure sine wave, I will get a beautiful response, right? Just when the second sample arrived, I know exactly what's the magnitude of this signal, and I know it without any error. Unfortunately, when I subject this algorithm to a real waveform, you will see that it's really not good. I mean, I will have a situation when I will overshoot by 100%. I will have situations when I will undershoot by 100%. This is not good. It's fast, but it's not good. So what I could do is I could apply longer data windows, meaning that I will watch that waveform for a longer time. And N here stands for the number of samples in a cycle. So N over 4 means that I am using quarter of a cycle window. So if the cycle is 16 milliseconds, I will use a window that is 4 milliseconds and do my best designing those filters to get the estimate. So now the ramp time is not instantaneous. It takes some time to really realize that the magnitude is not 0 but 1. And I have a slightly better performance. So here at least I don't overshoot by 100%. But again, this is not good. I could go on and make the full cycle algorithm right now. So I use 16 milliseconds of data. So now it will take me 16 milliseconds to make a full transition between old value and new value. So if my pickup setting was here, I don't care, I will still trip very fast, right? But if my pickup setting was here, it will take me 16 milliseconds to realize that the value is above the pickup, right? So this is how it responds to that distorted waveform. It's not bad. Here the error is because of CT saturation, unfortunately. That's not the fault of the algorithm. That's the function of that distortion which came from saturated CTs. And if my pickup is here, now to visualize how the relay works is we typically look, if we are running one cycle algorithms, we look at the one cycle of data from now to the past, right? We don't know the future, we only know the past. So as this data moves, what do we say? Trip or no trip? No trip, right? I mean, no matter how you crunch the data window, this current is definitely lower than the blue threshold, right? No trip. Now, shall I trip? Well, I don't know. I want to be a fast relay, right? I want to beat the competition, but then I don't want to trip when I shouldn't. Shall I trip right now? I don't know. Now, probably would say no. And time is passing, and eventually you realize that yes, you should trip, but that information is truly available only here. So this is what we try to do, right? We try to make decide whether the operating conditions are such that we should trip, assert the output. We want to do it fast, but we don't want to be wrong. We want to trip only when the conditions are that we should trip. Otherwise, people call it, rightfully so, a misoperation, and they complain about the relay. That's not that bad. If we trip and there is a blackout, then it's really serious. So that's what we try to do. Now, how much science is in it and how much it's heuristics? I would say most of it is heuristics. I mean, you have your science, you have your digital signal processing rules. You could use the cookie cutter approaches to design your filters. If a part of the design is to design a filter, you know all the toolbox, you have a lot of tools that you learn in school, how to design a filter to a given specification, right? You know how to estimate, full cycle Fourier magnitude. So all those bits and pieces, they are part of science. But there is a lot of heuristics and a lot of secret sauce and a lot of patents. So to summarize phasor estimation, typically what we have is we just use a pair of orthogonal filters. Sometimes we need the explicit removal of the DC offset. Many relays, they use Fourier. We use a cosine filter, which was a very clever thing in early days of relays because it allows you to save a lot of horsepower. Because actually you don't have to have two filters. You could have one filter and the other component is just the first one delayed by a quarter of a cycle. So to get the orthogonal component, you could do it via delay without calculating stuff. So using a cosine to get the direct component and using quarter of a cycle delay to get the quadrature component, that's a very good solution. It works as well as Fourier, but it requires only half of the horsepower compared with Fourier. People wrote tons of papers on Kalman filters and state observers, and it's just a fancy way to get information out of polluted signal. There is no big gain in doing it one way or the other. So I would like to show you an example or two, and I think we may have time for two, that illustrate that heuristic part of relay design, right? And the first one is breaker fail. Did you learn about breaker failure protection yet? Yeah. So what it is in high voltage systems, we duplicate relays, cabling, CTs, and so on, right? So you have to have two of them for availability. It also gives you this luxury that you could take one of the systems for maintenance, and there is the second one to protect your asset, and you don't have to shut down a transformer or a transmission line. So this is all good, except when it comes to a breaker. Breaker is too big and too expensive to put two of them. So we put one of them, we give it two coils to trip the mechanism with two different trip coils, but it's just one breaker. If it fails, that's it. So breaker failure protection is monitoring if a breaker was ordered to trip, did it really trip? If it didn't, the breaker failure protection operates. Now the question, what does it do? How to remedy a failed breaker? Who remembers? Yeah, trip breakers that are around it to cut the flow of current, right? So breaker failure from this perspective is very critical, because if you have a bus, and say those are the circuits on that bus, and those are the breakers, and assume that you order this breaker to trip, right? If this is a misoperation, what harm did we do? We just tripped that circuit. Maybe it's a feeder to a subdivision, maybe it's a small city, maybe nothing will happen because that city gets power through this line. We will reclose, nobody will notice, right? Now, if the relay that trips initiates breaker fail, so there is a breaker fail initiates signal to a breaker fail relay, and that breaker fail relay says breaker fail trip, meaning that yes, I detected that this breaker didn't really open. What do? We take that signal and we have to do this. We have to trip all those guys, because that's the only way to cut the flow of current towards that fault. So if breaker fail relay misoperates, we just made a big hole in the power system. We just took this entire bus. If this is a high voltage bus, a TV crew shows up and you are on the 6 o'clock news, right? And there is no reclosing on breaker fail trips. So breaker fail is a backup function. It needs to be very, very secure. So how do we detect a failed breaker? What's the principle that we typically follow? The principle is that we receive breaker fail initiate, meaning somebody who trips that breaker tells us, I just tripped that breaker. And then what we do is we take a current from that breaker and we measure if this current disappeared within a certain period of time. So if somebody told me that this breaker will take 3 cycles to open, I may wait for 3.5 cycles, and if I see a current, I will say this breaker failed to open. And I will assert breaker fail trip, and I will dump this entire bus. Right? So, is it complicated, breaker fail, as a function? Very simple. A timer and a single check. Is the current gone, yes or no? How difficult could it be, right? So, how much time do you think you will need to detect that the current is gone?
3 to 4 seconds.
From the moment the current is gone.
3 to 4 seconds.
So, if you look at the breaker current, so assume that we have a fault, right? So there is a fault current, maybe it's offset. We have a very fast breaker, it interrupted here. So maybe the relay tripped here, and we got a fast breaker at the 0 crossing, it interrupted, right? So this is the time that the current is gone. So how much time here do you think we need to realize that the current is gone? It sounds very simple, right? This is the problem. The problem is that in reality, what will happen is that current transformers may saturate. So when the primary current is interrupted, it's interrupted here. The secondary current, the current that actually relays measure, it's not 0. It's not going to become a nice flat 0 like here, right? So what will happen if we measured this current with something like a full cycle Fourier algorithm? This is what we will see. The same time, it takes some time to make a transition from pre-fault to fault, because what happens is that, any FIR filter is an averager, right? It does a weighted average of the samples within the window. So the window needs to fully slide from the pre-fault to fault to have the output making a transition from the pre-fault to fault. So the same dynamics that we have on the rising of that current, it will happen on the reset of that current, right? So it will take maybe a cycle to realize that that current is gone. Now, the difficulty here is that the threshold to declare the current gone is very, very low. This threshold in many applications would be below the load current. Assume that it's equal to a load current, so roughly 1 per unit, right? So this is the line that we have to go below for this element to drop out. But what is our starting point? Our starting point could be 20 per unit, because the fault current could be 20, 25 times nominal. So we have a long way to go. Now, the Fourier filter that we are using for a phasor estimation, what is the frequency it's tuned to? 60 hertz, right? In that subsidence current, that exponential decay that happens because of CT saturation, do you have 60 hertz? Yeah, you do. And we are looking for 60 hertz. So that subsidence current will delay, if I zoomed on that red curve, it will be there for a while because there is legitimate 60 Hertz component, right? So in this case, it may take me more than a cycle or two to realize that the current is gone. Can I live with this? Yeah, I may just set my timer to here, and that's fine. But what is the problem with that? I have a critical fault clearance time, meaning that my power station people will say that any fault needs to be cleared within 10 cycles or else we go black. So from here to my 10 cycles, I have to squeeze 2 trips. I have to make sure that I trip the main breaker and then I trip the other breakers. So under the contingency that the breaker failed, everything really ends after 10 cycles. Because if it doesn't, we go black. So waiting up to here to realize that the breaker fail actually opened is not an option. So we want to have a fast reset. So, what are the solutions? Use the filtered current, but it will take a cycle and a half or 2 to declare that the current is gone or it's not gone. So a brute force approach is like look for a holy grail. Give me an algorithm that will do it faster, right? Now, there were some really stupid mistakes in very early days of microprocessor-based relays. They used the RMS instead of filtered Fourier. If you look at the RMS of that tail, it's huge because you have this DC. If you do RMS, it will decay pretty much as the tail. So that was really a just total lack of thinking for some early relays. But even if you use the 60 Hertz component, the 60 Hertz component is there. Your filter is filled with 20 per unit values and it needs to slide all the way from the fault current to a post-fault after the breaker trip to realize that the output is not 20 per unit, is 0, right? So another idea was torque control, meaning that, and this is how the heuristics come into play, you don't let your filter to get filled with this high current. Because when you energize it all the way to 20 per unit, now it will have to take some time to realize that it's 0 per unit, right? So you hold the filter back, you fill it with zeros, and only start using real samples after the timer expired. So when my timer expired, say up to here, I start running that estimator and I say take a sample and see and run it through a Fourier. So if the current is gone, I will fill my window with zeros and the output I'm getting is zeros, right? So I will not let that kick coming from the fault to move my measurement instrument all the way to 20 and then complain that it takes so long to go back with the needle to 0, right? I will hold my instrument, don't let it go to 20, and when the timer expires and the system tells me, now go and check if there is a current, I will release my needle of my ammeter, and if the current is gone, it will stay at 0, right? So a smarter approach. But we could think of a special dedicated algorithm. So this is one of them. Let's look at the trajectory of the current. And what does it mean, trajectory? I could take the current and look at the derivative of the current. And when I plot those two things on a two-dimensional plane, I will make circles, right? It's AC is a rotating vector, so to speak. So I could go to this rotating picture, and what's the difference? If I have a fault current, that means that there is an AC source that drives that fault current, meaning that I keep rotating. I may be heavily distorted by the DC component or CT saturation, but the prevailing motion that I'm going to see is rotation. When I get to this point here, the current is not zero, could be far from zero, but it stops rotating, right? So how could I do that? So I could calculate two components. So, I could look at the very short window phasor estimator. So one could be a cosine part, a very simple filter with the window like this. Effectively, it's a smoothed derivative. And the other one is a smoothed current, or the average, right? And I could make those windows very short, for example, 1 or 2 milliseconds. Because I am not really interested in absolute precision of making anything. My goal is to distinguish between a rotating pattern and the exponential decay, right? So I will use two filters, very simple FIR filters, with these two windows, and I will convert my current into two components that I call IC and IS, and my window could be as short as 1/8 of a cycle. When I look at this current through my two components, this is what I will see, and how to interpret that. When I am before the fault, I am making a circle here, a small one, small magnitude, pure AC, right? When the fault happens, this is what I am doing. If this was a steady state perfect sine wave with no exponential DC component, I would be making a perfect circle, right? If I look at the sine wave and plot the sine wave against the derivative of that sine wave, I am making a circle. And then when the current is interrupted, around 7 cycles, my rotating motion stops, and I start resetting towards zero along the line that is shown in red, right? So there is a very distinctive difference between fault and no fault situation. So if I zoom here and then I put this vector as something that points to a given IC and IS coordinates, and I look at consecutive samples, I see that this thing is moving. It's rotating, right? It's not a perfect sine wave. It's not a perfect circle. It would be a perfect circle only if the input was a perfect sine wave. But at some point in time, it stops rotating and it starts decaying. So it moves like this to zero. So there is a persistent rotation and lack of rotation. So I could shape I could even do a little bit of science on this, meaning that if I assume that I am resetting this way with a single exponential time constant, I know what my second component is, and I know that the ratio is precisely a function of my time constant and the system frequency. So for example, I could be resetting along the line of 91 degrees. So there is a science how I'm going to reset. By the way, I'm going to reset two possible ways. So if my current was positive, the only way to get back to zero is to decay. So my derivative needs to be negative, right? If my current was negative at the moment of interruption, to reset to zero, the only way is to go up. So the derivative needs to be positive. So there is only two ways to get from that persistent rotation pattern back to zero, which we eventually end up with. It's either here or here. So what I will do is I will shape two cones. They are simple comparators. And I will run a timer checking how long am I within a cone. To shape a cone is just a linear calculation on the signals that I measure, right? So when I have a fault, I keep flying through those cones. So I enter, I start the timer. Before the timer expired, I am out. And I could pretty accurately estimate what's the worst time, how long I'm going to spend within that cone. It's going to be a few milliseconds. So I am in and out because I'm constantly driven by the AC source because the fault current is there. At the moment the fault current is removed, I stopped flying in and out and I reset this way. So this is the case when I have an extreme current transformer saturation, when that waveform is really distorted. When you look at the waveform, all this is effect of CT saturation. And what it does to my trajectory is that it's really not circular. It does, those funny things. But even when it does those funny things, I keep flying through those cones, in and out, and I don't declare the current gone until I am here. And now I start resetting this way, right? So when I look at the, so when the current is really interrupted, I never leave that cone and I reset within it. So my timer will expire and I will say the current is gone. The absolute value of the current is very significant at that point in time, but I already know that it's not driven by the AC source, that it's a subsidence current that came from the saturated CT. So this flag is basically telling me, you are inside one of these cones. So I'm in and out, and when the current is interrupted here, I stay. Oh, excuse me. I stay, and I never leave that cone. So I have a permanent assertion. My timer expires shortly after that, and this is when I declare that the current is gone. So in this case, my reset time is 0.4 of a cycle, compared with cycle and a half for a brute force other solution. So again, this is very good performance. Now, does it depend on any specific phasor estimators? I pick those sine, cosine, 1/f of a cycle. Do they have to be accurate? No. Do I have to spend months researching that part? No. It's just a sound heuristic observation that I use to decide whether I am dealing with alternating current, meaning the breaker didn't open, or I am dealing with the current that is not zero, but clearly is a fictitious current that is not coming from a generator that is supplying a fault. It's an artifact of a current transformer saturation. By the way, that current transformer saturation, there is two of them. Normally, we just blame the CTs and say CTs saturate. The truth is that it's a little bit of both. We have a CT inside our box, and that CT could saturate a little bit too. So that subsidence current, the fact that breaker interrupted at the zero crossing, and the primary current is dead zero, but we are not measuring that zero. The fault for that is the main CT out there in the switchyard, and a little bit is our own CT inside the box, the one that we put there for galvanic isolation between our electronics and what is happening in the switchyard. So that's an example of something that is, heuristic. There is part of it that is science, like I designed the filters, I understood what's happening, I have some timers, it's predictable, but part of it is secret sauce. And then when you consider how many functions we have in the relay, each of them may need one or two or three tricks like that, right? So it's a collection of various heuristic or semi-heuristic algorithms. We have time for, one more slide. So what are the observations for this breaker fail reset algorithms? That this is not a brute force approach. Because when you look at this, am I interested in the magnitude of the current? Is this what people paid for? No. The real question is, this breaker, did it interrupt the current, yes or no? The question wasn't about what's the magnitude of the current. The way to detect it is through measuring the current, but it's not about the magnitude of the current. I couldn't care less how accurately I measured at zero. It's kind of irrelevant because I am expecting to measure the zero, right? So it's not a brute force holy grail approach. The problem is defined properly, meaning that detection of the interrupted current is different than measuring the current magnitude. Only a brute force approach would be give me the magnitude estimator that is very fast. So I could just check it against the threshold and be done with it, right? We recognize the nature of the subsidence current, and that's one thing that is often applied in protective relaying, building devices that work fast and reliably, that you are dealing with a lot of signal distortions and error. And like in any, estimation theory, is the more you understand the error, the better solution you could devise, right? So understanding the nature of that subsidence current that is actually an exponentially decaying thing helps designing a good solution. And you end up with a fit-for-purpose algorithm. It's something that does one thing only, does it very well and very fast. You could use it in any place that you need to detect if the current is gone, yes or no, but it's a very narrow, fit-for-purpose thing, right? So that was the first example. We have time for the second one, so let me... how does it work?
Steve? You need a mouse, it should.
Okay. And the mouse is... I need to... I need to unhide those slides. And then this. You know what, let's keep it simple. Let's just view it in the edit mode for now. So the second example is external fault detection. So this is about differential principle. So you probably learned about the differential principle, right? So the Kirchhoff's current law says that you sum all the currents around a piece of apparatus and it's zero. If it's not zero, it means that you are not measuring all the branches. So there is an extra branch that was just created, and that's why the current is not zero. That extra branch is the fault, right? So if the current is zero, it's healthy. If the current is not zero, something is leaking. There is a branch created. It's a fault. We have to trip. Works like a charm. The strongest principle we have, except that we don't measure the currents. We measure the secondary currents, right? So if the CT is lying to us, it's saturated, it will create a spurious differential signal, right? So we have two connections. One is 10 amps, the other is minus 10 kiloamps, the other is minus 10 kiloamps. They sum up to zero. It's an external fault. But one CT tells us it's 10 kiloamps, and the other CT is saturated and says it's minus 8. We sum them up and we say it's 2 kiloamps. It's not zero. We should trip, right? There's different ways to deal with it, but one way that is very attractive in new relays is the external fault detection. Some people will say it's a CT saturation detection, and I typically ridicule that language because if CT is saturated, why are you telling me this? I need to know before they saturate. When they saturate it and you see symptoms of it, such as harmonics and what have you, it's already too late unless you intentionally delay your tripping so that you could give your CT saturation algorithm a chance to pick up. We don't want to delay anything, so what we are doing is we are building an algorithm for external fault detection. We want to know that this is an external fault, and if CTs saturate, we want to be prepared for that before they saturate. So, differential principle, all sum up to 0, no fault. If there is 0, if there is something different than 0, it's a fault. So, CT saturation, what it does is really the purple, the light color is the primary current, the darker color is the secondary current. They will differ because there is CT saturation, and the difference between the two of them, it will show up as a differential signal, as the operating signal, right? So we don't want that. So there is two types of CT saturation, really. One is that you hit the CT with such a high current that you are driving the flux in it so high that it will saturate after a few milliseconds, and that's it. It will choke effectively. The other type of saturation is that you have a relatively small current, but that current has a very long-lasting DC offset in it. And CTs, they don't like DC, right? They don't work on DC. They work on AC. It's a Faraday's principle. You have to keep moving the magnetic field to induce the output from the transformer effectively, right? So if you put a DC, what happens is that the DC component of the flux, it will go up and up and up because flux is an integral of the current, right? Effectively. So you have a small DC and it will get integrated up and up and up until it hits the saturation limit of the CT, and you start to see saturation errors. So this is a more dangerous type of saturation because it happens when the current is low. Normally what we do for CT saturation is we use the percentage restraint, meaning that if the currents are everywhere big, we increase the threshold, right? When the currents are low, the threshold is low, so if you have any error, it will come and bite you. So this is another heuristic algorithm that detects CT saturation. What happens here is that we monitor the change in the differential and restraining current. What is the restraining current? It's basically a sum of all the currents around it. So what happens if you have an internal fault? So let's assume that this is our protected element, whatever it is, transformer, bus, or line, and you have a couple of currents that you measure, and you have an internal fault. What happens is that there is sources everywhere, and all those currents respond to a fault. What happens to them? They go up. What happens to a differential current? It goes up, right? So if you monitor the changes in the differential and restraining current, this is what you will see. This kind of trajectory. I was sitting at 0 because that's a pre-fault. A fault happened, and the feeds that feed the current inside the zone, they went up, and the differential current went up, right? What happens if I have an external fault? So let me remove that fault and put it here. The fault current rushes towards the fault, correct? So what happens to all those currents? They go up immediately, right? So this is where the restraining current will increase. What happens to my differential current? The assumption is that a CT, even if it saturates severely, it saturates only after a few milliseconds. It has a room of few milliseconds, because what you have to do to saturate a CT, you have to move its flux from very low value all the way to saturation. And this cannot happen instantly, even if you put a lot of current into that CT. So saturation happens after a few milliseconds, and it starts producing a false differential signal. But before it happens, the sum of this current, this current, this current, and this current, known as the differential signal, is going to be 0. Right? Because the fault is outside, what's in, it's out, the differential current is 0. CTs are not lying to me yet. They tell the truth for the first 3 milliseconds. So the differential current stays low. So I see this move. Oh, there is a fault, and CTs start to saturate. So there is a fault. If CTs don't saturate, I stay here. And CTs start to saturate. So I see this distinctive pattern. So my logic works like this. If I see an increase in the differential signal, this is an increase in the differential signal. I subtract the value that is 1 cycle old. If I see an increase in the differential, so if I don't see an increase in the differential signal and I see increase in the restraining signal, for 3 milliseconds, I declare external fault. So this logic basically says, I see an increase in the restraining signal and no increase in the differential signal is an external fault. When I have internal fault, what happens, both of them go up at the same time. So this signal is logic 1. This is logic 1, so it's logic 0 here. This timer will never engage. So this thing will not pick up on internal faults even if I have a saturation during an internal fault. So it's truly an external fault detector. So it tells me after 3 milliseconds, you are dealing with an external fault. Get ready because CTs could saturate. So knowing that, I could adjust my countermeasures, I could become prepared for it, and I am not going to sacrifice sensitivity or speed on internal faults. Because on internal faults, this logic will never engage. This is how it works. I will skip that. The second type of saturation is DC saturation. So again, what that means is I have a current that is small, but it's offset. And that offset is not going away fast. So I effectively have a slowly decaying DC offset in this current. And what will happen is it will start saturating the CT, and I will start seeing that error eventually. So what will be the best way to detect that? Well, if the DC component, if the offset is the problem, why don't we measure it? How do I measure DC? It's an average over 1 cycle. Because if there is no DC, the sine wave goes positive and negative. If I average them over 1 cycle, I will get precisely 0. So a simple averager over 1 cycle gives me a measurement of a DC. So then what is it that I do? I will look at every current and I will say, this is the better way to show it. I will look at every current and I will say this. If a DC in a given current is greater than a pickup, and DC in a given current is greater than the AC magnitude in it, so I am saying basically DC must be non-zero and it must be significant compared with AC. If both those conditions are satisfied, in any of the currents that I measure for differential protection, and this happens for 3 cycles, I will declare an external fault. right? Now, there is more to it. I have an interlock here and basically says, and this is not an internal fault. So this comparator says differential is below restraining, which means this is not an internal fault. So if this is not an internal fault and I see a DC for 3 cycles, I will say, okay, that's it. If this was an external fault, I got 3 cycles to trip. It's not an internal fault. Let me get ready because those CTs are going to give up. I have a standing DC. I know they don't like DC. I have to get ready. Now, there is a ceiling loop here. When I declare external fault, I will maintain that declaration this way. Why is that? Because that DC will disappear. When one way of saying that, or one result of saying that CTs don't like a DC component is that they will not pass it through. So what will happen is that waveform, its offset, when the CT saturate, it will center itself. I mean, CTs will not pass direct current. So that direct current will disappear on me. So if I am looking at the direct current, I will drop out. That logic will drop out, which I don't want to do that. So I have to seal it in or go on a long timer to the tune of a second or something, knowing that this thing will settle after a second or two, and I will go back to my normal sensitivity and normal situation. So again, what this example showed is, do I use anything fancy? Did I spend months researching some Kalman-based estimators? No, I used a simple thing. How do I measure DC? Just average it. How do I measure that AC magnitude? Anyway, I mean, this is not a fast thing. I wait for 3 cycles. I know that those CTs are not going to give up on me that fast. It will take a while for that DC to kill my CTs. So I have time to deal with it, right? And this happens very often on generator relays because near generation, your X over R ratio that dictates that DC time constant is huge. It's 90 or 70. It also happens on generators when you pick up a transformer. When you pick up a transformer, it draws an inrush current. Inrush current is not bidirectional. It's offset, and it could last for a second. So recently, NERC mandated the exercises, the black start exercises, meaning that you assume that there is a blackout and you restore the system to normal. And one of the things that you do is you energize a transformer from a generator. And then people realize that generator relays are tripping, misoperating left and right. And why is that? Because the transformer inrush current has a long-lasting inrush, DC. That DC causes saturation, and generator differential function misoperates. One of the things that I designed years ago was precisely this algorithm. And the way we found out was that small generators that were put left and right, they were put by 2 different engineering companies, and they would put such different CTs and such underrated CTs that anything happened and you started having CT errors and problems. So we solved it this way. So again, it's a very custom, fit-for-purpose approach to the problem. So to wrap it up, I hope that I made you realize that when it comes to building those devices, there is system engineering approach required. When you think about it, it's a relatively complicated device. It does a lot of things. Some of it is measurement, some of it is protection, some of it is communications, some of it is protocols. There is fiber optic ports, there is Ethernet ports, there is those secret sauce algorithms that run in it, right? You need protection engineers. I mean, in this lecture alone, we were talking about FPGAs, DSPs, Fouriers, flux in CTs. You have to connect the dots to really build something meaningful. So this is the role of system engineers and protection engineers. You need to have mechanical engineers. It's not trivial. You cannot just clad it in a chassis and call it good. Right now, there is so much requirements on heat dissipation, vibration, and other things that you really need to have state-of-the-art mechanical design. And what happens right now as the toughest requirement is design for heat dissipation. You start clocking that silicon so fast, and you are not allowed any fans in it, and you need to withstand operating temperatures of 80 degrees Celsius, that it becomes not trivial to do the mechanical design. Hardware, of course, firmware, software, you have to have software to set it up. There is a big communications aspect to it. There is testing. A few words on testing. So there is a couple of types of tests that we do. One is performance testing. And what performance means is we build a distance relay. How well does it do distance protection? So you expose it to realistically looking currents and voltages, different lines, different operating conditions, different sources of errors, things like CT saturation or errors in the voltage transformers. And you want to see what's the speed, what's the sensitivity, what's the security. Is it going to misoperate? How accurate is it, being fast, and so on. The way it's done is we run typically closed-loop testing. So what you have here is, this is a bunch of relays. Those cables are I/O interfaces. This is a specialized computer by the name, the company is called RTDS, which stands for Real-Time Digital Simulator. This is basically a small supercomputer that runs model of the power system in real time with a timestamp of roughly 50 microseconds. So it solves the differential equations that describe a big power system, and the output is voltages and currents that the relay would see. So those go to high fidelity amplifiers, and then the output from the amplifiers goes to relays. When the relay trips, we send the signal, the trip signal, back to the simulator. The simulator has a model of the breaker, and it will start modeling the breaker as it opens. So this way, you could simulate a lot of relays, a lot of faults, and you have a closed-loop situation. When you place a fault, some relays should detect it. They will open the circuit breakers, and on top of that, you could have 50 other relays that see all of that, and you watch them if they don't operate because they shouldn't, right? So that's the beauty of closed-loop testing. That equipment, by the way, it's pretty expensive. Those 3 racks would be probably $600,000, which is not a.
Next year they will have it here, I think.
Oh, that's good. The price tag is different for universities. Yeah. For manufacturers and utilities, this is not that expensive. What is expensive is really train somebody or 2 or 3 and be able to run those studies. So it's a very nice piece of equipment. The other aspect is emissions, interference, and all of that. So radiated emissions is that equipment. I mean, there is an agreement between a couple of parties. So one party is people who build substations. They have to make sure that the environment is quiet enough. So they have to meet certain requirements that if you put a relay there, those relays are not going to reboot every 2 minutes, right? So it's about proper grounding, proper shielding, proper distance from the primary conductors. Then we design relays to withstand that environment, but also those relays shouldn't emit too much noise because that affects other things sitting nearby. So I cannot do anything I want because, 10 inches away from my chassis, there could be some other relay or some other meter, and I cannot harm it to the point of rebooting it every 5 seconds, right? So I have to limit my emissions, and believe it or not, that becomes a problem because you are clocking so many things so fast, you are driving so many Ethernet ports and other communications ports that you become a noisy device. Believe it or not, the requirements are that you have to have a certain spectrum. They check a certain spectrum and the energy that you are emitting. In one of the products, what we had to do is we had to intentionally keep moving the clock, a microprocessor clock, to spread, because if you clock it at a certain frequency, what happens is you have a frequency spike in what you are emitting, right? So what we did is we move it. So then it's the same energy, it's just over a wider period. It's a crazy thing, but sometimes you have to do things like that. The length of the leads that we have to put certain things in cages and shield them because we are emitting. This is our old lab. Right now we have a lab that you could bring a big truck in it and it will fit in the new building. So we are investing in that equipment. Transients, things couple through wires. So there is a standards, IEEE standards, how you hit the device with various transients and it should survive, it should not misoperate, and so on. Electrostatic discharge, especially for ports, there is humans there, we walk, we wear clothes, so, we could bring electricity to those connectors, so you have to shoot them with certain energy levels, and the thing should not only survive, it should not reboot, it should not trip the breaker, because, things happen. This is the other fun that we have. You may think that this picture is not in focus, and partially it's true. The reason that relay is not in focus is because it's vibrating. This is a vibration test when you basically stress the device for vibration. Why do we do that? There's a couple of reasons. Some utilities, they have to follow the seismic requirements, like in California, for example, when there is a real danger of earthquakes. That was a big problem for electromechanical relays because they do have moving parts. This thing doesn't have many moving parts. There is one, the output. You could get rid of it. You could put a thyristor instead of the clicker, and there is no moving parts. But, that also is good for transportation, meaning that if you build the device properly, you know that on a FedEx truck is not going to get destroyed. Handling, and also it checks the overall ruggedness of the design, that components aren't flying off the boards. What we do in manufacturing, we follow a burn-in process, meaning that if something is wrong, if a wrong part got populated, or there is a part defect, or somebody on the Monday morning shift got too much fun over the weekend and they didn't follow the procedures, that we want this stuff to fail in our factory before we ship it. So what happens is we put those relays in the oven, we cycle temperature very fast, from very cold to very hot. What happens to a printed circuit boards, they really are stressed. If there is a poor quality solder or other defects, they will show up and the devices will fail. And this way we will not ship them and we will not cause a problem to anybody. So in summary, I didn't mention that before, microprocessor-based protection was a very disruptive technology, and the reason we have it today is reduce the cost by the factor of 5, literally. A high-end electromechanical relay panel for a transmission line used to be worth the same as a good car. And right now you could buy a relay for $5,000, less than that. Improved functionality, relaxed limits to operating principles, extreme flexibility of application, late point identification. You don't have to imagine old days. What happens is you don't have settings. If you wanted a relay that operated a certain way, the way to get it was to pick the right model. And then they shipped it to you weeks after, and that's it. You better get it right. Right now, all of it is numbers. It's numbers that you punch in your setup program that runs on a laptop, right? I would argue that microprocessor-based relay design, it's an exciting field. It's highly specialized. It's multidisciplinary. A lot of it is secret sauce of our patents, but it's really fun to be able to do that. And I think that's the last slide.
Any questions? How long do you warranty these for?
That's a very good question. So what we have is we do have a warranty. And I don't even remember what it is. And the reason you have to have a warranty is that legally you have to state your warranty. So I don't know.
Right, so 10 years, but I have said
10 years. But what happens is we never charged anybody, not a single case, for repair or replacement. What we say is you bought a product from us 30 years ago. It's technologically obsolete. You send it back, we will take it and we will give you a new one. And that's true. That's what we do. And the reason we do this is that that's the only way to learn about failures and improve your designs. So as a result of that policy, and people don't abuse it. I mean, you bought a product 30 years ago. It worked for 20 years. You are replacing it for other reasons. You're not going to send it back. But some people do. But the result is that we inspect and track what fails, and we learn from that. So our mean time to failure numbers, how long does it take for a relay to fail, are to the tune of 500 years. So you buy 500 devices from us, and statistically only one of them will fail over a period of 1 year. That's probably 4 times higher than industry average. So, the life cycle, people expect those things to last for 15 years. Our relays last more than 15 years. Right now, there is probably a need to change them because of technological obsolescence earlier. And what I mean by technological obsolescence is you need a better function. You need a new protocol. You are changing this stuff anyway. So that's the reason to replace it. They will last close to 20 years, our relays. But we are probably best in class right now because of that policy. Other manufacturers, they are moving towards the stated 10-year warranty. But I really don't remember. I think it's 10 years, but it doesn't matter. We take pride in it. We tell everybody that's the case, and we walk the talk. That's what it is. You bought a relay from us. We take it, no questions asked.
Yeah, I have sent 1 or 2, right? Not many. That doesn't indicate a good thing if I'm sending too many things back. But I have never seen them. If I send one, then they get, if that is a very old one, you get a brand new one, replacing it. Or they just fix it and send it back within a week. If it is a major critical item, they send a spare relay for us to mount it, and then they return it. After they fix it, you can return that. Any other questions? Just you want to know that he has how many patents? I don't know how they think.
20 something, yeah.
And I know over 200 papers. And it's a great honor for me to have known him for many years through IEEE, and then we do interact quite a lot. We worked on many standards, and we have argued, discussed, agreed, disagreed, but we have always maintained that professional respect for each other. Thank you, Bogdan. And he has his cards.
Yeah, I have a couple of cards. If you are interested in internship or things like that, and again, you don't have to be a protection engineers. Most of our people are hardware designers, programmers, FPGA specialists. So feel free to take card, and if you are interested in any questions or any internship opportunities or employment opportunities, let me know.
Thank you very much.
Thank you.
I have a silent sheet there. Somebody in the back.